So in this lecture we'll be talking about the optional stopping theorem. It's a very intuitive statement. It has some subtleties, but in the end it's something very intuitive and very useful. We are essentially saying that whenever you see a deterministic time in a statement about a martingale, you can replace that time by stopping time. I'm not being very precise here, but in along the lecture you're going to see what I mean. So let's start with sub-martingale xn. And let's recall some facts about it. So for example, if we have Hn a predictable process, then the process Hxn is also going to be a sub-martingale. Okay. Not only that, we could use this result for examples of predictable process. For example, this indicate a function that n smaller than t for t a stopping time. We already did this, right? To obtain that the expectation of xt, sorry, let's take a stopping time that is bounded, uniformly bounded. The expectation of xt minus x0 is the expectation of hxk, because this process h is going to jump together with x until time t, and then it's gonna stay still. It's not gonna change anymore. So at time k, this will be just the telescopic sum that gives xt minus x0. And since this is a sub-martingale, this is bigger than the expectation at time 0, which is 0, because this is a incremental process. So in particular, the expectation of xt is larger or equal than the expectation of x0. So what am I trying to convey here? You remember that for sub-martingales, we knew from a long time ago that for deterministic times, the expectation of sub-martingales would grow. And you see here, this statement is just replacing this deterministic time by a uniformly bounded stopping time. And this is the type of result that we are looking for in this lecture. So we start with a technical result, because what we want to do now is replace this boundedness of the stopping time here. So we don't want to take stopping times that are uniformly bounded, because of course in several situations we want to deal with unbounded stopping times. And for this we are going to need the following technical result. So suppose that we have xn a sub-martingale, and suppose also that it's uniformly integrable. Take t a stopping time. Now we don't need it to be bounded anymore. Then x and t is also uniformly integrable. So this is a technical theorem that says that we can translate uniform integrability to this stopped process if t is a stopping time. This is going to be useful later for the optional stopping theorem. So let's go to the proof. So here we know that xn is a martingale, so is xn plus, right? Sorry, submartingale. We're just composing it with a convex and increasing function. Moreover, let's analyze what happens with the expectation of xn minimum t plus. So this is a submartingale. This is bounded, this t minimum n is a bounded stopping time. If t is a stopping time, t minimum n is also a stopping time, but now it's bounded. So this is going to be smaller or equal than xn plus. And this is finite, right? Because this is in L1, this lives in L1. And we have that xn is not only in L1, but it's uniformly integrable. So this is also uniformly bounded across n. So we can take the supremum in n of this, and it's also going to be smaller or equal than k, which is finite. So now we have this process here, which is a submartingale as well. And it's uniformly integrable. Sorry, its expectation is uniformly bounded. So that means that it converges almost surely. So xn minimum t converges almost surely to some variable x. And now I'm going to take some time and rename this variable x to xt, and I explain what I mean by this. So t is a stopping time, right? And when we take this random variable here, we should be written like this to be more precise, right? T of omega evaluated at omega. When we evaluate t at omega, we get a time here, a proper time, and x at this time is a random variable, and then we can evaluate this random variable at omega. Now the fact that this converges to a random variable, x, whenever t is finite, this random variable is going to be equal to this random variable here. You first evaluate t at time omega, and then you put an omega here. Because when on the event that t is finite, this as n grows is going to stay at t omega for some longer times. So this is going to oscillate until it hits t, and then it stays flat because the minimum between n and t is going to be t. So this is going to be t for every n larger than t of omega. So in the end, what I'm trying to say is that it makes sense to call this xt. It's a good notation for the almost sure limit of these random variables. Or you could try to think of this as the t minimum infinity. Now, another result that you may have forgotten, when we have a submartingale that has the positive part bounded in expectation, we have the almost sure convergence, and we also have that this limit belongs to L1. We don't have L1 convergence, but the limit belongs to L1. And we're going to use this now to finally show that this process here, x n minimum t, is uniformly integrable. To do this, we have to calculate this expectation, estimate this expectation. And the way we are going to do this is to split into two cases. So either we are taking the same expectation and n is smaller or equal than t. This is an event, right? Or the same expectation, but n is strictly larger than t. And why are we doing this? When n is smaller or equal to t, n minimum t is going to be n. So I can put just xn here, xn here, and that's it. When n is larger, the minimum is t. So here I can just put xt, indicator that xt is larger or equal to m. So this is an equality. And now let's copy this to the next page. We can bound this equality by the same thing without the indicator functions anymore. So in the end, we used this indicator function of n smaller or equal to t just as an auxiliary stepping stone. And there you go. Why is this interesting? Recall that xn was assumed to be uniformly integrable. So we can take m large enough so that this will be small uniformly over n. And remember also that xt is a random variable in L1 because we obtained this from the limit of submartingales. So this means that here this random variable is a family of a single random variable that is uniformly integrable. So you can also take another m large so that this is smaller than epsilon over 2. So together, this gives us the result. So this is a technical result. It allows us to translate the uniform integrability of a submartingale to the uniform integrability of the stopped submartingale. This is also going to be a submartingale. Okay, with this result at hand, we can now prove a first result in the flavor of optional stopping. So this is going to look nice already. So take X a submartingale and let's assume it's uniformly integrable. So you see, before we were assuming that the time t, the stopping times were bounded, and now we're not going to take bounded stopping times anymore. We're going to take t smaller or equal to s, two stopping times, but we'll no longer assume they are uniformly bounded. They could even take values equal to infinity. It's not a problem for this theorem. Then the expectation of x0 smaller or equal than the expectation of xt, smaller than the expectation of xs, smaller or equal than the expectation of x infinity. Why can I talk about x infinity? Because it's a uniformly bounded martingale. So a submartingale that's uniformly bounded, that's uniformly integrable, converges. So we can talk about this. This is just the limit as n goes to infinity of xn. So again, I'm going to emphasize that we already knew this result if we were talking about deterministic times. So this was clear from the beginning. And what we are doing now is extending this to stopping times. So the proof is actually going to be very, very simple. We have, by the fact that n minimum t is bounded by n, we already know that the expectation of x0 is smaller or equal than the expectation of x n minimum t, which is smaller or equal than the expectation of x n minimum s, smaller or equal than the expectation of xn. This follows simply by using the right predictable processes. So here we are going to use the predictable process n smaller than t. Here we're going to use n smaller than s, and here, sorry, t n between t and s, and here n smaller than s. So this we already know because all of this is for finite n. So this is uniformly bounded. This is uniformly bounded. So we have no problem for this. But now recall that xn is uniformly integrable, right? So it converges almost surely. N in L1. Also, xn minimum t is also uniformly integrable because of the previous theorem. So it's this uniformly integrable. It converges to xt almost surely n in L1 because it's also a submartingale. So this is also a submartingale that is uniformly integrable. And the same is true for n minimum s converging to xs. Now we just look at this inequality that holds for every n, and we take the limits. First here, then here, then here, and we get the result. So just have to take the limits one by one, and the inequality is going to be preserved, the limit. And we can take the limit because all the convergences happen in L1. So this is indeed a very simple proof. This is just translating a result we already knew for finite stopping times to the infinite ones using the uniform integrability. And now, before we are able to state our end result is the optional stopping theorem, we have to talk a bit about sigma algebras generated by a stopping time. So we have talked a lot about sigma algebras like this, right? This is our filtration, which is nothing more than an increasing sequence of sigma algebras. So the more the time elapses, the more information we have. Now, we had an interpretation for the sigma algebra in terms of someone in a room playing some game. So you are inside some room, some game is happening, people are throwing dice or revealing cards, and you can observe all this information, and Fn is all the information you obtained until time n. Now, we also defined t stopping time, which is just a random time for which this belongs to Fn. Sorry, t smaller or equal than n belongs to Fn. So we have studied these stopping times in detail, and they have an interpretation as well. This is some sort of random decision that you can take without looking into the future. So it could be we gave an interpretation in that room as, for example, the time you decide to leave the room. So you are there looking at cards being revealed, and maybe you say, okay, I will leave the room as soon as some card is revealed, maybe the 10 of spades. When I see that card, I will leave the room. This is a stopping time. Or maybe you say, whenever the coin shows head 3 times in a row, I will leave the room. This is a stopping time. And what we're going to define now is Ft, which is going to be intuitively the information that this person has. a person that left the room at time t, it gathered some information, right? It's not some fn, because t could be n or could be bigger than n or smaller than n. So this is going to be a sigma algebra. So there's no randomness here. It's a sigma algebra associated to a random variable. And its definition is going to be this. It's all the events such that if the event happens and t is smaller or equal to n, then this is known by someone who knows fn. So let's try to give an intuition here. We have some person that is leaving the room at time t, a random time. And we have another person who's leaving the room at time n. Let's call this Alice, and let's call this Bob. What this says is that if Alice knows something, so A belongs to Ft, and Alice left the room before time n, then Bob knows the same thing. So for example, let's say that Alice is leaving the room as soon as she sees the 10 of spades. So for example, one such event could be the 10 of spades appeared in an even time. Okay, this is a normal event. I mean, if Alice leaves the room when a 10 of spades appears, and the 10 of spades appears in an even time, she will know that. She will know that the leaving time is even. And if this happens and t is smaller or equal to n, this is going to be also known by Bob. In this case, it's clear. If t is even and t is smaller or equal to n, we can write this as a union of t is equal to j for j smaller than n and j even. So it's clear that this belongs to Fn. So Bob, who left at time n, also knows this information. So I'm not going to extend too much into the intuition of Ft. I'm just saying that Ft represents the information gathered by someone who only observed the system until time t, a random time. And another important observation, we talked a bit in Probability 1 about Fx, the sigma algebra generated by some x. This is a different notation. Ft means something different. This is the precise definition. And what we're going to show now is that Ft is in fact, by the Ft defined like this, is a sigma algebra. If it's not a sigma algebra, we cannot make much with this, right? We cannot take conditional expectations, we cannot even take unions of events here and be there. So the first thing we have to prove is that the empty set is there. This is obvious, because the empty set intersected with something is the empty set, which is in Fn. So this is fine. Now the difficult part is going to be the complement. So suppose that A belongs to Ft, which implies that for every n, A and t is smaller or equal to n belongs to Fn. And we want to understand what happens to A complement intersected with t is smaller or equal to n. So let's make a small picture here. Here we have A and A complement. Here we have t smaller or equal to n, and here we have t larger than n. And what we are interested in is this area here, A complement and t smaller or equal to n. What I'm going to write is actually very obvious if you look at this picture. This is just A intersected with t smaller or equal to n complement. Complement. So let me first draw this region. This region is this. right? It's the small square a and t smaller or equal to n complement. But we are also intersecting with t smaller or equal to n. So look at the picture above and see if you agree that a complement intersected with t smaller or equal to n is this. Can be written as such. So now we know that this belongs to Fn, so its complement also belongs to Fn. And we know that t is a stopping time, so this is also in Fn. So we are done. A, for every n, a complement and n smaller equal than t smaller equal than n is Fn measurable, so we are done. And now the third part is going to be actually easy. Suppose that we have a family AI of events in Ft. So that means that for every n, for every I, AI and t smaller or equal to n is in Fn. Okay, so if all of these events are in Fn, their union is also in Fn. I'm taking the union like this. This is in Fn. But observe that here there is no I, so we can take the parentheses out. And since this holds for every n, we have that the union is in Ft. So yeah, that was the full proof that Ft is a sigma algebra. Now we are ready to give the final result of the martingales course, which is the optional stopping theorem. So what it says is, suppose xn is a submartingale and which is also uniformly integrable. Observe that we can replace the uniform integrability of the submartingale by the boundedness of our stopping times, but we don't want to fix ourselves to bounded stopping times. We want to take general ones. So suppose that s smaller or equal than t smaller or equal than s are stopping times. And they could also take value infinity, it's no problem. Then the expectation of xs given ft is larger or equal than xs itself. Again, it's very important to observe that we already knew this for deterministic times. So if s and t were deterministic times, this would be true. It's a simple calculation. For s equals t plus 1, sorry, for t, sorry, it's all wrong here. So here should be t, I'm sorry. So here is t, and here is small t. So again, if s is just t plus 1, then this is the definition of, is in the definition of submartingales. But for any s larger than t, this is also true for deterministic times. And what this theorem is saying is that it generalizes to stopping times as long as x is uniformly integrable submartingale. So now let's go to the proof. So for the proof, we need to integrate things with respect to the sigma algebra, right? So we're going to start with some event in Ft. And the way we're going to prove this is by constructing another stopping time. And it's going to be a stopping time that is heavily dependent on this special event we chose. it's gonna be t on the event A and s on A complement. So our probability space can be partitioned in A and A complement. We have a random variable defined in the whole space and another random variable defined in the whole space. We just use one of them in A and the other in A complement. And the first thing we're going to show is that n is a stopping time. Or in other words, that for every n smaller or equal than n belongs to Fn. So how are we going to do this? Let's decompose this event. This is what we're proving now. Let's decompose this event into two pieces. So either n smaller or equal than n, and A happened, this is one possibility, or n smaller or equal than n and A complement happened. Why am I splitting it like this? Because now I can replace n by its definition in each of the sets. In case A happened, n is just n is just t. In case A complement happened, n is just s. Good? Now, this is easy. Remember that A is in Ft. What does it mean? It means that A and t smaller or equal than n belongs to Fn for every n. Great, so this is exactly what we have. This belongs to Fn. We are getting close to proving that this is a stopping time, right? The problem is S is not, A is not in Fs, which is what would give us for free this. We are having a problem here. We know that A complement is also in Ft, but it's not in Fs. What we're going to do actually is to rewrite the above in a trivial way. Recall that S is larger or equal than T. So if S is small, T is also small. So we are not changing anything by writing T smaller or equal than N. But now, let us swap these two. A complement belongs to Ft. So it means that the intersection of this and this event belongs to Fn, because A complement is in Ft. And S is a stopping time, so this is also in Fn. So this whole intersection is in Fn and the whole thing is Fn. So we just proved that n is a stopping time. Okay, now we are going to finish the proof of the optional stopping theorem by calculating simply the expectation of xn. So xn can be written in two different ways. We can recall that it's decomposed as either xt on the event A or xs on the event A complement. That's the first way we can decompose xn. Now, remember that we have a uniformly integrable submartingale. And by the previous theorem, we know that if a stopping time is smaller than the other, the expectation is also smaller, right? So here, this stopping time n is sometimes t, sometimes s, but in both cases it's smaller or equal to s. So this is smaller or equal than the expectation of xs. Now the expectation of xs can also be decomposed in terms of A. This is xs in A or xs in A complement. And now we just cancel these two guys. And we obtained what? That the expectation of xt on the event A is smaller or equal than the expectation of xs on the event A. That's almost what we want. Let us just take here here inside this expectation, we're going to take the conditional expectation given ft. Let's see what happens. So here we have the same xt in A, but here we will have the expectation of the conditional expectation of xs given ft. We're supposed to have an indicator function of A here, but A is in ft, so we can always take it out of the conditional expectation. So in the end, this comes here, and this holds true for every A in ft. So in the end, what we have is that this xt is we are proving that something is the conditional expectation of xt given ft. So we're proving that the expectation, this what is here, right, given ft, is the conditional expectation of xt given ft, because this is the formula, is bigger or equal than the conditional expectation of xt given ft, because this is the formula that defines the conditional expectation given ft. But now xt is measured with respect to ft, so this is just xt, and we proved our formula. So this finishes the proof of the optional stopping theorem. And just before we finish, let us look into examples of what the optional stopping theorem gives us. So for example, imagine that we have a martingale which is bounded, for example, between 0 and n. An example of this would be a random walk that stops whenever it hits 0 or n. Okay, so let's define this precisely. x0 is some h. Let us not use n here because we used n for stopping times. Let's put here okay. So x0 is h, some integer, and xn plus 1 is xn plus some IID random variables with distribution delta minus 1 plus delta 1 over 2. So this is just a simple random walk. And let's define the time t, xt. Define the time t is the first time for which the random walk is either at 0 or at n. And we know that xn is a martingale, so is xn minimum t. So this is the process that I pictured here, is the random walk running until it hits either 0 or, it's not n, this is k, either 0 or k. So this is uniformly integrable, although the first one is not, because this is bounded. Okay, so that means, for example, that the expectation of xt is equal to the expectation of x0. What I'm using here is just the two sides of the inequality. Since x is a martingale, x is a submartingale. So what is in the left is larger or equal than what's in the right here. And since x is a martingale, minus x is also a submartingale. so that we get the other inequality. So joining the two, we get the exact equality. So this, as we saw, is h, is the starting point. And what is xt? So h is equal to the expectation of xt, which is sometimes it's sometimes 0. Sorry, sometimes it's 0 on the event that it hits 0 when it leaves the interval. Sometimes it's h when it hits h when it leaves the interval. Sorry, not hk. And it could be that it never hits neither 0 or nor k. So it could be xt on the event that t is equal to infinity. Now, there are several ways to show that this does not happen. So, but we already proved that every random walk hits 0 with probability 1. So it definitely cannot avoid the time t. So the time t is finite almost surely. There are other ways to prove this that don't even involve martingales. It's very easy to show that t is finite almost surely. So we only have these two situations. This is when the random walk hits 0 before. So this is saying that at the hitting time it's at 0, and then it's 0. And here it's saying that it hit k before. So in the end, what we're getting is 0 plus k times the probability that xt is equal to k, which in the end tells us that the probability that xt is equal to k, is equal to h over k. So this is a very nice simple formula. The random walk is something complex, but what it's saying is that if you start at height h, the probability that you hit k before hitting 0 is linear in h. It's just h over k. If k is, let's do some simple calculation. If h is equal to k, that is 1. Of course, if you start here, you already hit here. If h is equal to 0, that's 0. Of course, if you start here, you're already stopping here. And in between, it interpolates linearly. So this is one example of how we can apply results of that are true for deterministic times using random times. We can use this to calculate probabilities of certain events, like in this case, the probability that you hit k before you hit 0. And we can also use this to estimate various other events concerning a submartingale. So there will be more examples in the exercise list, but for now, that's it. Thank you.